everyone, this is M, and today I am with my co-future engineers Claire and Christine to discuss to you two topics with regards to highway and railroad engineering. The first topic is the main type of methodologies in the assessment of desirability and economic and environmental or social aspects of constructing a highway proposal. And then the second one is the basic elements of highway traffic analysis. To discuss to you the first part, here is Christine.
Cost-benefit analysis utilizes the net present value technique where the cost and benefits of the scheme are discounted over time so that they represent present-day value. Identifying the main project option. This is a fundamental step in the CPA process where the decision maker compile a list of all relevant feasible options that they wish to be assessed. It is usual to include a to-do-nothing option with an analysis in order to gauge those evaluated against the baseline scenario where no work is carried out. To-do minimum option offers a more realistic course action where no new highway is constructed but a set of traffic management improvements are made to the existing route in order to improve the overall traffic performance. Identifying all relevant costs and benefits. The application of cost-benefit for project assessment in the highway area is more complicated by the wide array of benefit associated with a given road initiative. Some easier to translate into monetary values than others. Many of the benefits of improvement to transport project equate to decrease in cost. The primary grouping that contains this type of economic gain is term use benefits. Primary grouping benefits. Reduction in vehicle operating cost. Saving time. Reduction in the frequency of accident. Secondary grouping benefits. Accruing to non-user of the proposed facility. Number 1 is positive or negative changes in the environment. Number 2, loss of improvement of recreational facilities. The cost associated with the proposed highway installation can fall in a similar categories. However, in the most evaluation sufficient consideration, construction costs incurred during initial phase building, maintenance costs incurred on an ongoing basis throughout the life of project, economic life residual value, and discount rate. A highway project is often complex and long-term, cost and benefit associated with it occurring over a long period of time, which we term the life of project. It is usually 20, 25, 35, and even 50 years or more. The cost and benefit occur at different time zones over this time horizon. Hence, they cannot be directly combined until they are reduced to a common time frame. This is achieving using discount rate, which translate all cost and benefit to time equivalent values. The actual value used is the social discount rate, given that the decision maker is interested in the benefits cost to the society, not to any individual or group of individuals. The discount rate is opportunity cost of capital in the public sector. The World Bank has not calculated a discount rate for each project but has 10 to 15% as a notational opportunity cost of capital developing countries. Economic indicators and basic economic viability. The MVP will estimate the economic worth of the project in terms of the present worth of the total net benefits. The IRR will give for each option under consideration, rate at which the MVP is equals to 0. Benefits over cost ratio based on the ratio of the present value of the benefit to the present value of the cost. All the three methods depends on the discounting rate to the arrive at final answer. Assuming a discount rate of 10%, the project will economically acceptable if NPV at the net benefit at 10 is greater than 0. The IRR is less than 10% or the benefit over cost ratio at 10% is greater than 1. The most straightforward method involves choosing the option with the maximum NPV of net benefits. Advantage and the use of the common unit of measurement money facilitates comparison between alternative highway proposal and hence aid the decision-making process. It offers a broader perspective than a narrow financial or investment appraisal concentrating only on the effects of the project to the project developer. Disadvantage: the method is more suitable for comparing highway proposal design to meet a given transport objective rather than evaluating the absolute desirability of the project isolation.
From the discussion of Christine? Well, it's for sure that you've gained additional knowledge from her.
And for now, let us move on to the second subtopic, which is the environmental appraisal of highway schemes. When we say environmental appraisal, it is the act of evaluating or assessing first the highway project plans considering our environment. We all know that in cost-benefit framework of highway projects, it makes no attempt to value its effects on the environment, mainly because its purpose is for the transport efficiency and safety. So in this topic, we will talk about considering the environment from the very first stage, which is the highway planning. This procedure started in the US during 1960s when environmental issues gained importance. Environmental groups lead the way to identify the need for environmental assessment within the project planning process. All the possible and avoidable environmental impacts of the proposal and what would be the alternative options to this proposal with its short-term and long-term effects aid the identification and evaluation of all impacts relevant to the highway project. So, the question is, what are those environmental impacts forming the assessment framework that I am pertaining to? Well, the first one is the air quality, which we all know that a vehicle causes air pollution. Then, the cultural heritage, like the issues of demolition of archaeological remains, monuments, and buildings, which may cause effects to the heritage of a specific locality. And we also have the construction disturbance, though this impact is just temporary. We also have the nature conservation, because highway being proposed has negative effects on a certain wildlife species and to their habitats as well. For example, Certain animals may die because of losing their homes due to vehicle emissions. Next is effects on landscape. Local landscapes may be altered by the project construction. Traffic noise and vibration must also be considered due to the number of vehicles using the road, may it be heavy or not. In fact, vehicle vibration may also damage buildings' fabric as well. Pedestrian, cyclist, and community effects in terms of increasing the journey time and breaking the links between them. The services or facilities that they are using every day, like their workplaces, schools, and shops, are also evaluated. And lastly, the policies and plans compatibility with the highway development plans at local, regional, and national level. Each plans was subjected to a new form of assessment, which is our next subtopic, the new approach to appraisal or the NATA. This new approach is incorporated with both economic appraisal and environmental assessment, wherein all impacts, like what I have said earlier, should be measured and made sure that the assessment reflect the number of affected in additional to the impacts. This new approach of appraisal, all the impacts economically and environmentally are being summarized into environment impact, impacts on economy, accessibility, and integration.
So for basic elements of highway traffic analysis, we have these properties wherein dito mini-measure yung highway effectiveness. For speed, flow, and density of a stream of traffic, we can compute for the traffic flow as shown in the formula, which is Q is equal to N over T. Q is the traffic flow, N stands for the number of vehicles in a given time interval. And also, we can compute for the number of vehicles by using K is equal to N over L, wherein K is the traffic density, N is the number of vehicles, and L is the length of roadway. So the three parameters, the traffic flow, space, mean speed, and density, are directly related under stable traffic conditions. So from the formula, Q is equal to UK, so nakikita na natin yung basic relationship nilang tatlo. For speed, density relationship, so this is straightforward and easy to explain when compared to other fundamental relationships. So according to this graph shown presented by green shields, the speed-density relationship is linear with a negative slope. Therefore, as the density increases, the speed of the roadway decreases. So the speed reaches approximately 0 when density equals the jump density. So the general form of green shield's speed-density relationship can be expressed as this, wherein C1 and C2 are constants. Well, it is also possible to have nonlinear relationships between speed and density as shown by the dotted lines. For flow-density relation, so the flow and density vary with time and location. So according to this graph, it suggests that the only time there is free flow speed is when the density approaches 0. So at this relationship, the density at maximum flow ay may formula na Km is equal to Kj over 2, wherein Km, the density at maximum flow, is thus equal to half the jump density Kj. For the speed-flow relationship, so the relationship between the speed and the flow can be postulated as follows. So the flow is 0 either because there are no vehicles or there are too many vehicles so that they cannot move. So at maximum flow, the speed will be in between 0 and free flow speed. So from derivations, we've come up to this formula. Qm is equal to Uf times Kj over 4. So here is an example problem. You can pause the video para mas mabasa niyo yung problem. So in here, hinahanap yung maximum flow of the traffic stream. So yan, meron yung group 1 daw has an average speed of 45 km/h and group 2 has an average speed of 40 km/h. So para makuha natin yung K value, so divide lang natin yung vehicle per hour over the average speed. So yan, meron na tayong K value for group 1 which is 30 vehicle per kilometer, and group 2 K value is 45 vehicle per kilometer. So, para magkaroon to get the consequent relationship between the speed and density, we are going to use a coordinate geometry. So, yan. So, para makuha natin yung slope, so, speed over density, so, meron tayong negative 1/3. So, the slope M is negative 1/3. So, examining the boundary conditions, we are going to have a free flow speed. Examining the boundary conditions, we're going to have a free flow speed of this value, a jump density, and the maximum flow. Now, let's proceed in determining the capacity of a highway. So, there are two different approaches to determine the capacity of a highway. So, the first, which can be termed as the level of service approach. So, the second approach is the approach for rural roads. For the level of service approach, it is described in a qualitative way the operational conditions for traffic from the viewpoint of the road user. So the Highway Capacity Manual in the US lists 6 levels of service ranging from A, which is the best, to F, which is the worst. Meron po tayong Service A, free flow, Service B, reasonably free flow, the presence of other vehicles noticeable. So, light decline na in the level of convenience and comfort. Sa Service C, stable flow. So, near free flow speed but noticeable restriction. For D, approaching unstable flow. So, yan na, bumabagal na siya. So, for unstable flow, operating near roadway capacity, minor disruption can cause delay. So, for the last, and the worst, or system breakdown, forced flow. So, ito na yung breakdown in vehicle flow. Ito natin dito sa graph yung speed and flow relationship na kung saan yung level service A, diba, speed is near its maximum value, while dun sa level service D, na maximize na siya. Yung level of service F, nakikita naman natin na if denoted the breakdown condition. Meron din tayong mga definitions na dapat i-familiarize. So, meron tayong hourly volume. So, yun yung the highest hourly volume within a 24-hour period. The peak hour factor, or PHF. The next is the service flow, or the SF. The peak 15-minute flow, or V15, enlarged to an hourly value. Part of the level service approach, let us discuss the maximum service flow rates for multi-lane highways. So, the Highway Capacity Manual generates maximum flow values obtainable on a multi-lane highway given a certain speed limit and prevailing level of service. So, dito, meron tayong values na ina-assume with ideal conditions that exist. And sa part pala na to, the driver population consists of regular weekday drivers, and the road is divided by a physical barrier and rural base. Given the existence of ideal conditions, we have a formula, SF max. So, yan. Ito na yan. So, wherein yung SF max dyan, yan yung maximum service flow. N is the number of lanes in each direction. CJ is the capacity of a standard highway lane for a given design speed, J. So, yung values na yan ay ito sa table. Makikita natin yung values of CJ for different design speed. So, magagamit natin yung mga yan later on sa ating mga examples. And also, meron din tayong table for the maximum ratios of flow to capacity for each level of service and design speed limit. So, yan. Let's have an example for in this area. An example problem in maximum service flow rates for multi-lane highway. So, pakibasa na lang po, viewers. So, here we are asked to determine the level of service being provided by the highway. So, first, kunin muna natin yung service flow. So, makikita naman natin sa given yung sa problem yung mga given or in problem. So, since sabi dito, ang design speed limit daw is 70 mph. So, meron tayong C70 is equal to 2,000 passing. So, paano ko nasabing 2,000? So, according dito sa table 4.1, so siya ay 70. So, ang CJ niya is 2,000. So, from our formula, so, transpose lang natin kasi ang hinahanap natin is ito, level of service. Then, input na natin yung data. And, so, yan, na-input na natin yung data. So, nagkaroon tayo ng design speed of 0.58. So, kunin natin yung table 4.24 reference para malaman natin yung level of service. So, yan. So, since siya ay C70 and ang sagot natin is 0.58, so yung the ratio of flow to capacity is greater than this one but is less than 0.71. So, ang level of service natin ay C. Ideal condition, so this is the formula to be used wherein yung FW is the adjustment factor, FHB is the correction factor, and FP is the driver population. So, later, may mga ipapakita ko sa inyong table na kung saan sinasaad doon ang mga values na ito. So, for the passenger car equivalent or the PCE, so may kanya-kanya tayo. Ito yung number of equivalent private cars that would occupy the same quantity of road space. So, meron tayong PCE for trucks, buses, and recreational vehicles. So, ito are defined for 3 different classes of terrain. So, we have the level terrain, rolling terrain, and mountainous terrain. Kung na to, makikita natin yung passenger car equivalents for different classes of heavy vehicles. So, yan. So, pag nagkaroon na tayo ng PCE valuations, the overall correction factor can be estimated once the percentages of the 3 vehicle types present along the section of road in question has been arrived in it. So, yan. Meron tayo dito ang isa pang formula, which is the formula for the correction factor. So, if the driver population is deemed not to be ideal, example, hindi siya composed entirely of regular weekday customers, so the capacity will be reduced by anything between 10% and 25%. So, dito naman, makikita natin yung table for correction factors for driver population. So, yan. And also, the correction factors for highway environment, yun yung FE. So, itong mga table na to is magagamit natin mamaya for our example. So, yan. Let's proceed na dun sa example. For our example, a suburban undivided 4-lane highway on rolling terrain has a peak hour volume in one direction of 1,500 vehicles per hour with the peak hour factor estimated at 0.85. So, all lanes are 3.05 meters, so there are no obstructions within 1.83 meters of the curb. So, yan, given dito yung percentages for the heavy vehicle types, and we need to determine the level of service of this section of highway. So, unang gawin natin is, ilista muna natin ang mga given. Or pwede na dumiretso tayo sa computation muna for the service flow, since na alam naman na natin yung hourly volume during the peak hour and the peak hour factor. So, we have So, yan, nakuha natin ang SF as 1,764.71 vehicles per hour. So, meron tayo dito ang design speed na 600 number of lanes in each direction, which is 2. For the adjustment factor, so since na siya ay 3.05 meter wide and no roadside obstruction, we can proceed to the adjustment factor table. So dito, makikita natin yung 3.05 meters. Distance of obstruction na given is 1.83. So, from 3.05, so meron tayong adjustment factor of 0.91. We can also solve for the resulting reduction of FHV. So, yan, makikita natin na may PT, PB, at PR na tayong given. So, convert na lang natin siya sa decimal form. Dito naman sa ET, EB, and ER, so, we can proceed to table 4.3. 4.4, I mean. So, yan, meron tayo dito table 4.4. So, since sabi sa given ay rolling daw. So, yun. Type of terrain natin is rolling terrain. And, eto na, magkakaroon na tayo ng value for the correction factor. Okay. So, for the ideal driver population and dun sa FE, so sa FP, makikita natin yung correction factor according sa driver classification dito sa table na to. So, yan. Since yung problem natin is for regular weekday commuters, so meron tayong correction factor na 1.0 and correction factor sa highway classification, sinabi rin na suburban siya and it is undivided. So, suburban, undivided, we have 0.80. Since nabanggit ko kanina yung formula nito, so gagamitan natin siya para makuha natin yung design speed. So yan, naipasok na natin yung mga given and nagkaroon tayo ng value na 0.92. So para malaman natin yung level of service nito, edi proceed tayo sa table for level of service, which is this one. So yan. So kita naman natin na, di ba yun ay VC 60, C60. So, ang nakuha natin is 0.92. 0.92. So, less than 0.80 but mas malaki pa yung 1.00. So, dito tayo sa E. Level of service is E. Service flow rates for two-lane highways naman tayo. So, for example, if a driver wishes to overtake a slower moving vehicle, the opposing lane must be utilized. So, this is the formula, SF divided by 2,800 times V over C. So, the ideal conditions assume the following. So, if ideal conditions were obtained, so the service flow is obtained using the ratios of flow to capacity associated with the required level of service. So, dito makikita natin sa table na to yung level of service values for two-lane highways under ideal conditions. So, for conditions naman na non-ideal, so yung the capacity of the highway reduces from 2,800 private cars per units per hour based on the following equation. So, dito, we have the table for correction factor for different directional splits on a two-lane highway. Ayan. So, dito naman, the correction factor for non-ideal lane widths and clearances from obstructions. So, yan, this table, yan, passenger car, equivalent for different classes of heavy vehicles. Now, let's proceed to the next example. Finally, since yung design hourly volume natin is a two-directional flow, tulad ng AADT, the flow of peak direction is estimated by multiplying it by a directional factor D. So, yan, DDHB is equal to K times D times AADT. So, para mas maintindihan natin to, let's try an example. And for this problem, so yan, pakibasa na lang. You can post the video para mas mabasa nyo maigi yung problem. So, So we are asked to calculate the service flow when running at full capacity. So since the road is operating at capacity, the level of service is assumed to be E. Therefore, we have this. So yan, may value na tayo dito na FW and FD. So you may proceed to this table para mas malaman nyo na, sige, tama pala yun. Pagdating naman sa car equivalents for different classes of heavy vehicles, since dun sa given is level siya, a rolling, yung type of terrain, so, and may level of service siya na D or E, so, kukunin lang natin yung tapatan nila. So, ito yon. So, yan, makukuha na natin yung adjustment factor niya, yung FHV, using yung mga given. So, yan, pinasok natin yung given na nagkaroon tayo ng 0.657. So, para makuha naman natin yung service flow, so, using this formula na diniscuss ko kanina. So, yan, pasok ulit natin yung mga given na na-compute natin. So, we will going to have an answer of 1145 vehicle per hour. Next one is sizing a road using the highway capacity manual approach. So, when sizing a new roadway, yung a desired level of service is chosen by the designer. So, within the US, it is common practice to use a peak hour between the 10th and the 50th highest volume. So, dito, in order to derive this value for a highway, the annual average daily traffic or the AADT for the highway is multiplied by a term called K factor such that, so yan, ito na yung formula for the design hourly volume. So, yung K, so dito, sabi dito, more usual daw ang K30 figure na gamitin. Kasi it implies that the road will be over capacity 29 hours per year. Masya, because nagkakaroon siya ng better utilization of economic resources. And finally, since yung design hourly volume natin is a two-directional flow, tulad ng AADT, the flow of peak direction is estimated by multiplying it by a directional factor D. So yan, DDHB is equal to K times D times AADT. And for our example problem in sizing a road using the highway capacity manual approach, so ito yun. Again, you can pause the video para mas mabasa na siya ng maayos. So yan, for the directional design hour volume, so I use the formula K times D times AADT. So ito is K30, so yung sabi ko kanina is equivalent siya sa 0.12. So yung directional factor niya naman is 0.6. Ito yon, and the AADT is 40,000. So meron tayong DDHB na 2,880 vehicle per hour. So, we can calculate the service flow kasi alam na natin yung hourly volume and the peak hour factor. So, yan, using the given sa problem, meron tayong SF or the service flow na 3,200 per hour. Vehicle per hour. So, dito, inassume lang natin ang mga values nito para makuha natin yung number of lanes using this formula. So, yan. Pasok lang natin ulit yung given and we are going to have an answer of 2.25. So, rounding up tayo. Kaya yun ay 3. So, meron tayong 3 lanes na required in each direction sa problem na to. And lastly, for the estimation of AADT for a rural road in its year of opening, undertaken using the factors supplied in this table. So, yan, nakikita natin dyan yung low and high growth forecast for 5 different categories of road traffic. So, it is used in conjunction with present-day AADT figures to produce future flows. So, these are then matched with the appropriate AADT range in this table. So, makikita natin dyan yung flow ranges for different classes of rural highway. In order to choose the right carriageway type, so traffic growth factors ay issued siya sa COBA manual. So, this document contained the traffic growth profiles over the years 1981 to 1996 along with forecast of low and high traffic profiles for each year from 1997 to 2031. So traffic was split into 5 categories. So what are those? So we have the cars, yun, kasama na yung taxis, minibuses, and camper, vans. Next is the light good vehicles, so all car type vehicles, all delivery vans. Other good vehicles, so yan, either 2 axles with twin mirror tires, 3 axles rigid. So next is the other good vehicles, so all good vehicles with either 3 axles articulated or 4 or more axles. So lastly, we have the buses and coaches. So yan yun yung mga buses and minibuses with the capacity for more than 6 passengers. So doon sa table na pinakita ko sa inyo kanina, doon sa low and high growth forecast for 5 different categories, ay it gives the traffic growth rates from 1997 to 2031 is a UK forecast. So yung document na yun, inassume nila yung zero growth post ng 2031. So the values is in annual percentage rates rather than expressed as an index. So the average percentage of each vehicle type within the UK during 1994 was as shown in this table. Yan, nakikita natin dyan yung percentage of different vehicle classes in UK for 1994.